Good afternoon. Second session of the ReverseIt course. Today we will start talking about equipment. That is, what do you need to effectively, in terms of equipment, to do reverse engineering. First of all, the modern reverser toolkit. We identified some levels. Basic level, which is something you must have if you want to effectively do reverse engineering, is at least a screwdriver with inserts, like the iFixit one. The more inserts you have, the more stuff you can open. This because any of the devices out there has its own kind of screws. They have torques, tamper torques, the classical screws. They have triangular screws. There is everything. And I think that the best way to be able to really open whatever you want, in some sense, is to buy a screwdriver with inserts, such that you can, at any time, you can choose the tip you want, based on the screws you have to remove. Another important tool is a soldering iron, also basic one. I mean, you do not need, wait, I have to take one thing. You do not need super fancy soldering station with multiple soldering point tips and whatever. Just a basic soldering iron with a fine tip. We will see why do you need a fine tip. It's enough, and this is what I was taking. It's a flux pen. It's a pen of liquid, which allows you to easily solder things, because you have the soldering iron, you have the lead, how can I say, yeah, let's say the lead to solder, but you need a flux pen if you want to attach, for example, fine wires on components. For example, if you want to probe some signal, the best way to do it is to solder small pieces of cable on the signals you want to probe, which are basically, and very often they are GPIOs of some microcontrollers or stuff like that. You need flux pen just to make the soldering process more easier. Otherwise, you can incur in the risk of destroying your board, basically, because only having the lead and the wire is not enough. You need something which allow chemically to easily add or remove the lead. Third thing you need is a spool like this, of very thin 30 AWG, which is American wire gauge cable. I do not exactly in terms of square millimeters, it's very thin cable. I will give you an example soon of how this cable can be used. This cable is very useful because you can use it to effectively to probe signals without the need of clips, the risk of making short circuits, everything. You just solder this wire on the signal you want to probe. You put better small drop of hot glue to keep everything still, and then you can probe your signal. The middle level is improve your simple soldering iron with a basic soldering station with, if possible, hot air. This can be really useful if you want to remove components, for example. You have, and this is quite common, you have, for example, a memory chip. You want to see the content of a memory chip without having to turn on a microcontroller. You can have an example of this if you look at the reverse engineering process of the famous Amazon Dash button. The Amazon Dash button has an external flash memory in which there is a copy of the firmware. The guy who reversed the Amazon Dash button effectively desoldered this memory from the Amazon Dash button and connected it to an ad hoc board to probe the signals, to read the content of the memory without having to turn on the microcontroller. And to do this, it's strongly suggested to have a hot air station to be able to desolder chips with many LEDs, with many shapes, with whatever. If you have an hot air station, it's a tool for basically desoldering everything. Advanced, we add to the middle, which was the one before. We add the microscope, either optical one or USB one, like this. This is a USB unit which you can connect to the computer. I have also another unit which is completely electronic. Is this one. You do not even need to connect that one to the computer, but it's really useful for when you have to deal with components with very little LEDs, with little pins, like let me think, like LQFP packages. We will see one of them in a while. Screwdrivers. If you have it soldering station with the air gun, do not forget the flux pen, always present, always necessary, always of help. A microscope, if you want. If you don't have a microscope, you can still access the signals in other ways, for example, by scratching the paint on the PCB. Okay, another useful stuff, if you want, is a set of clips or probes to attach on the, for example, on the memory chips. There are available those clips which allow you to directly connect some probes on the pins of the chips without the need of soldering. So if you want, you can, up to a certain point, substitute the soldering station plus the microscope with those clips. But remember, up to a certain point. There are chips which are very tiny, and for them for sure you need a microscope. Another thing which is really important is, we put it as a pro level, but it works as always as a remember, is an ESD wristband or kit, which is needed to ground yourself. Grounding yourself is very important before doing anything on electronics, because if you have, for example, a wool scarf, or you you have just walked on a wool rug or whatever, you can have an electrostatic potential on yourself, and you risk to discharge this potential, which turns in voltages of around tens of thousands of volts on the board you are trying to reverse engineer. And those discharges are very devastating for the electronics. I mean, you have something which is designed to work up to 3.3 volts, for example, and you are discharging on it like 10,000 more. It's something which is for sure is not healthy for the electronics. So before opening and doing something on electronics, if you do not have the ESD wristband kit or kit, which is, okay, it's like a Cadillac for reverse engineers, at least remember to touch a door, metal radiator, something which is firmly connected to ground, your car, don't know. But always remember to discharge yourself before touching electronics. Otherwise, you incur in the risk of destroying everything. Okay, now, once you have your tools, the first step is to disassemble your thing. Pro tips. First pro tip, if you are disassembling something which, I mean, is the first time it's the first time that someone is disassembling it, please take good pictures, like the ones you will see shortly, because other people can use your pictures if you share them. I mean, it's not mandatory to share them. It's good if you can to share them. Take good pictures if you can, put annotation on those pictures, but because those pictures can be really, really useful for other people which use, for example, your reverse engineering efforts for building something new. So if you can, take good pictures. Other stuff, always remember to, this is the radio. I wanted to do live disassemble, but unfortunately I do not have the right screwdrivers. I forgot. Anyway, always remove battery, power, and things like those. Search for visible like those screws. Remember that there is the possibility to have some screws under stickers. This is not the case, but you see here there is a label. There is the possibility in some devices that there is a screw behind this label. Also, if you are in doubt, in some sense, remove more screws than you think is necessary. I know that those two screws cannot be removed, those two, and you can open the device only by using those two. But the first time I removed those two once and those two once. Another important thing is if you have removed all the screws and you find that opening the device is very difficult, do not make force. I partially broke a radio because I forgot to remove hidden screws, and I forgot to remove those screws, and I forced the opening and I broke. Luckily, this is not a huge damage, but keep in mind that if the radio or the device is not opening, there is something which is preventing this opening, and you have to better investigate and search for this something which is preventing. An example in this case are those rings here, which around the antenna connector there are two rings also behind these knobs, which are used for sealing. You have to keep in mind that there is a possibility that in your device there are some of those rings for sealing and something, and you have to make sure you have removed everything before trying to opening the radio. Another point, keep in mind that there is the possibility that there are some cables connecting the two parts. Again, I cannot show you, unfortunately, but this radio opens in two pieces. One piece holds the keyboard and the LCD. The other piece is this metal heatsink plus the electronics, and there are two cables connecting those two parts. So just not tear them apart with violence, otherwise you incur in the risk of destroying some connections, because those connectors are not designed to withstand huge forces, for example. Another point is that sometimes you can have to deal with some kind of device which is glued. In this case, an heat source like a soldering station, hot air soldering station, even a hair dryer can be helpful to loosen the glue and then to open the cover. Again, be careful when applying the heat, because you can, for example, you can modify the shape of plastics. The majority of devices are made of thermoplastic, which is something which is plastic which becomes soft when heated. It becomes soft the first time you inject it in the mold, and it still becomes soft each time you apply some heat to it. So be careful when applying this kind of heat.
Also, other components which are sensitive to heat
Hi.
are hi Silvano, are LCD panels. They are very sensitive to heat, so heating them up to maybe 50 or 60 degrees might break them, and a little less heat sensitive, but still even more dangerous when they are damaged, are batteries. If you have some raw cell battery, you know, the one which resemble like a little silver bag or a black bag, if heated up, they might explode. And really, you don't want to have, you know, to make your battery explode, because that will cause a lot of smoke, that might hurt you, that might catch fire. It might trigger a fire alarm if you have one in a building, and you know, it's something you really don't want to do. So a heat gun is a powerful instrument and should be used cautiously. Go ahead, Silvano.
Another point about batteries. If your device has embedded batteries, like, for example, an iPod, you do not have access to the battery. An iPhone also. I'm not an Apple user. just to cite a couple of them. When opening it, be really careful to not puncture the battery. Lithium-ion batteries, in this sense, are like really bombs. Because lithium-ion batteries are devices which have a very high energy density, and they are like at the limit of stability in terms of chemistry. So if you by mistake puncture lithium-ion cell and you make a short circuit, okay, that cell goes boom in really short time. Okay, let me think about other stuff. Other thing that about thinking about my experience of something I read around. Keep in mind that some devices can have some kind of anti-tampering mechanism. For example, you want, because you are curious, you want to do some security research, you want to open like point of sale device. Keep in mind that such a device can have some anti-tampering mechanism which can trigger a mass memory raise, for example. How to circumvent those stuff is like, I would not say rocket science, but it's very, very difficult. But anyway, if you have to deal with something like that, keep in mind that there is the possibility that you, by opening the device, you are exposing yourself to the risk of losing some of data which reverse engineering. But if you have more than one device of this kind, okay, you in some sense you destroy one to not destroy the other ones. But anyway, just to give you an idea of what you can encounter when you are disassembling stuff. Okay, now identifying components. Unfortunately, I was not able, sorry, to open my radio, but however, thanks to people who, and to another stuff I have here, thanks to people who made some pictures before, I can show you the internals of the radio. Before showing the internals of the radio, I want to show you another board. To do this, I have, no, sorry. Let me see, I can use VLC. I can show you other stuff with my USB camera. Okay, here it is, beautiful picture of my table. Okay, here it is, microcontroller. I have this development board here from ST Microelectronics. This is a microcontroller. Here it is. This is the LQFP package. It has those really beautiful pins which you can use to probe data, to probe signals. You can use the Kinner wire, in this case, in this way, with the soldering iron. You remove the plastic on the Kinner wire. You put the wire, let me see if I can, oop, here it is, probably it's coloring my view. This is 30 AWG Kinner wire. If you see, if you look, it has the more or less the same size of one pin of the device. So you can just put this like here and then solder a cable. Let me see if we can reach more easily another GPIO. Sorry, but it's not the best board to work on. I just want to show you an example. I'm not soldering it because it takes a lot of time. But okay, you just have to put. You need steady hands. You do not have to drink coffee if you are sensible before doing this kind of work. You see, This wire has the exact same size of one pin, so you can put this on the pin with flux, with your soldering iron, and solder this one on the pin, and then you get access to the signal. We did this, and I will show you the logic analyzer's traces of some signals we probed when working on MD UV380 radio, which is the band
First,
sister of mine.
Let me clarify one thing, Silvano.
Yeah.
You know, some of you might wonder, why do we need to solder wires? Can we just attach an SMD clip on the pin itself? Well, technically you can, but since the pins, and even more than the pins, the solder pads on which they are soldered to are very fragile, most likely you will end up bending the pin and raising up the solder pad on which it is soldered. And I can tell this because it happened. And
Also to me.
it happened. So if you want to probe signals and you don't want to spend several hours trying to put back a solder pad, please do solder Kinner wire on top of the piece.
Also, once you soldered it, put always a drop of hot glue either on the soldering point or at some point near the soldering point to keep the wire steady. And always remember to not insist too much on the same point with the soldering iron. Otherwise, you end up destroying the pad on which your pin you are probing is connected. And if you rip it off, okay, the board is done, and you cannot anymore probe the signal unless you take the painful way of trying to reconstruct the path. Anyway, what we also see here, which can be useful for probing, if you do not want to solder, let me see if I have a little stick to point stuff. Oh, coming. Let me take a pair of tweezers and use them as a pointer. Okay. If you do not want, to solder stuff here on the GPIOs, you have those holes, which are called vias, and are used to route a signal from this face of the board to the opposite one. We can flip the board and find the end of those vias. Now, I do not exactly know which is. It should be this one. Those ones should be. So those vias are used to route signal from one phase to the other phase. And if you gently, with a cutter or something, if you gently scratch off, you can try the green paint here. This is not quite scratchy, but anyway, if you scratch away the paint, you can solder the Kinner wire either here on the via, so on the hole, you have to scratch away the paint, or another point on which you can solder, which is also easy, is directly on this connection, the so-called track. For example, you can scratch away the paint here, paying attention to scratch paint only away from track and not here on this solid part here, which is ground. Then you put flux, and then you can solder your wire here on this piece, and you almost do not need the microscope. You can do this if you want with your phone camera or with with a lens if you want. Okay, going on. What we have here? This is microcontroller, easy. Also keep in mind that very often the chips tell you who they are. They have a part number, which is firmly engraved on the body. This is STM32F103. Let me rotate it for better reading. Okay, STM32F103 C86 microcontroller. However, keep in mind that there are chips which are very, very small, like this one, and they carry basically no information about who they are. How do you understand what do they do? By analyzing the rest of the circuit. In this case, it's near to a USB port. If you follow the traces, you can find that this is connected to the USB port, blah, blah, blah. I take it for short, it's a voltage regulator. It's just a case, right? Because for example, on the radio, this kind of chip is either a voltage regulator or an analog switch for switching signals around. And you can understand this only by analyzing the rest of the circuit. Another thing we have here, this small blob with almost not readable part number. Let me see if I can focus. This one should be, because I know in advance, an accelerometer, but I'm not sure. Then those brown stuff, those brown beads here, those are for sure capacitors. For sure, they are capacitors, ceramic type capacitors. Then you have those bigger yellow ones. Those are still capacitors, electrolytic type, another kind which have a grid capacity. And then those black stuff here, this is an inductor, this is a resistor. If you do not have the label, which is which, if you have a tester tells you which is which. You put one LED of the tester here, one LED of the tester here. If you have something like hundreds of ohms, it can be either a resistor or an inductor. If you have something like thousands, 10,000s, and more ohms, okay, it's a resistor. Standard or common, yeah, I think standard label for inductors, R for resistors, C for capacitors, and U for integrated circuit normally. Okay, what there is also, okay, this light emitting diode if you want. D stands for diode. LD stands for light emitting diode, or light emitting diodes are also labeled as D in the same way because they are diodes. Some type of resistors like these are for, let me flip it if I can find it again, where it is. Okay, these R4, it's for sure a resistor. It carries an indication of what is its value. 224 stands for 2.2 multiplied by 10 to the power of 4. which is 22 kilo ohms, if I remember correctly the labeling, but I mean, you can find it on internet if you want. I mean, it's quite common, but and this is also another way you have to distinguish between inductors and resistors. Inductors, like, almost never have a label on them, while resistors have a label. Then, to move back to our radio, we have this guy which made those internal photos of the radio. And if you are in the lucky case, like our case, and you have the schematic, you can, by looking at the schematic and looking at the hardware, the real hardware you have, the photos, whatever, you can identify the parts, for example. Just to make, okay, here we have microcontroller, big one, STM32 again, which is here on the schematic. You have the same name here, which is written on the device. Schematic, what tells you? Tells that this shape is capacitor. This is value. It's another way to code the value. It's a bit nasty. Anyway, this shape is a resistor. Then you have connection. This is the crystal, which gives the clock signal to the microcontroller. It's very, very common that microcontrollers have a crystal device, quartz crystal for clock. There is an additional crystal at 32.768 kilohertz, which is standard for the real-time clock. So by looking at this, you can deduce that there is a real-time clock inside this microcontroller, and this is used for something. And keep in mind that all those clues you can get from the schematic or by observing the board are a useful guide when you are looking for when you are going through the binary, that is the program that is stored on the microcontroller, for example. So if you have the schematic or by looking at the board, you can extract valuable information to understand what pieces in the firmware do. For example, the function of each GPIO, you can trace the tracks here and try to understand what they are doing by looking on hardware and looking on software. Keep in mind, however, that like this radio, there are devices in which the PCB has some hidden parts. For example, let me see if I can sketch it a bit. For example, we have a layer which is called the top, which is what we see here is, for example, is this layer, okay? Then we have the bottom, which can we access, is this one again. And then we can have at least other two hidden layers. Let me draw them in blue. Okay, here, but they can be up to 16 different layers. And keep in mind that some connections can go from the top to this internal bottom with a via, go around this intermediate layer, and then go up again, or from this can go directly in the second hidden layer, or from these can go down here. So if you follow a trace, you encounter a via and you, on the back side, either you do not find the via in the exact position, or you see that the via is connected to nothing, okay, then we have a problem, and the problem is that this via is connecting a signal on the top face with something, with some path in the hidden layers. And okay, when you have a situation like this, you have to understand what the signal is carrying and to make hypotheses on where you can find it again on either the top or the bottom side. Keep in mind that there are no components here in those hidden layers. There is no possibility to place components in the middle here. Since these are like less than 1 millimeter, there is no possibility to place hidden components.
And once you have done an hypothesis, you can test it using the multimeter again in diode mode, which is the mode. Maybe I can pull my. Well, I will fetch my multimeter meanwhile.
Okay.
Go ahead, Silvano.
Okay. Okay, so going on with our exploration. This is a battery. I mean, it has a shape of a battery. It's quite easy. That's a crystal. It's one of the possible shapes for a crystal. That's a memory chip. This is SOIC. I do not remember the acronym, but stands for something. There are clips available for those. You can put the clip here and probe the signal directly. This is another crystal. This is the basement chip you find here in the schematic, for example. Here you have the connectors for audio. This is the connector for the speaker. You see it because there is a cable which goes to the other side of the other half of the radio. So from that you can say, okay, that's one. This one is connector for speaker. You see that is connected here. This is the connector for speaker. This is for sure connector for microphone. You can deduce it. So this can be, for example, an amplifier used for microphone stuff. This can be another amplifier just by deduction. Going on the other side, you have, okay, here you have a lot of radio frequency stuff. You search for 72310, this one, and you find either on internet because you do not have the schematic, or on the schematic you search for this. Here it is, phased locked loop. In this case, this is used for control of main clock frequency of the radio, the transmitter frequency. So if you have the schematic, okay, you have great aid. If you do not have the schematic, either you have to go on the hard way, and so probe everything, look at firmware and make hypotheses based on firmware and so on, or keep in mind that at least for those cheap radios, keep in mind that the internal structure is always very similar among different types of radios. Okay, so you have MD380, this one. You have the schematic for this one, but you do not have an MD380. You are wanting to, you want to reverse engineer an RT3S radio, another kind. You open it up, you see that the logic side is quite similar. They have the same MCU, they have the same memory, they have, I don't know, the same piece of hardware here. Then there is a great probability that the radio you want to reverse engineer has at least some pieces of the hardware which are exactly equal to the radio you do not want to reverse engineer, but that you have the schematic for. So by comparing and by difference, by using the schematic, you can trace the things you know because you have the schematic, and by difference, you can identify and see the other, for example, the other GPIOs for which you do not know the exact function, but you are exploring for example.
So meanwhile, I fetched the multimeter. So
okay.
the setting to check the contiguity is the sound of a small, the sound of the icon of sound of the beep.
Oh, okay. I get it.
And in this one in particular, I have a select button to be able to actually identify that mode. And once you have selected that, you will plug the two probes, and by touching the probes together, the multimeter beeps. So the cool thing is that if you want to check whether a certain PCB line actually connects the two components that you have hypothesized, you can touch with the two probes the two components, and you will know whether you have contiguity. But this is one thing which is also useful is to check for grounded pins. You can do that by connecting, since in every device all the grounds are connected together. You can with one probe attach to a metal part of the device. For example, the shield of a USB connector, or a screw, or a metal housing, and because they all will be connected together. And then with the other one, you can probe different pins and different traces to see if they are connected to ground. And this will be nice because if you have to identify, for example, the orientation of a component which has no clear marking on the pin, or even if, for example, you have a set of pins and you have to guess which protocols is running there. If a pin is tied to ground, then there's no chance it will run a signal. So you know that will be the ground. And one small thing which is outside of the topic of the course, but equally important. So this course is was organized by POuL, which is an organization recognized by the Politecnico di Milano, and therefore the Politecnico di Milano asks us to for a proof of the fact that actually some people attend our courses. And so please, if you did attend, please do fill in the self-certifying document which says that you actually attended this course, and submit it back to the form. We need this to be able to provide courses like this in the future. So please do that before the end of the course, or I mean, just don't forget to do that. And please go on, Silvano.
Okay. Okay. After a bit of dive on the hardware side, and before switching to effectively to firmware loading, reverse engineering, and this part, I want to show you how and what kind of shape they have in time. The signals you can probe. I mean, how those signals are. For example, I have here a set of logic analyzer captures I took from another reverse engineering of another radio. I can open. Let me. I have it. I have it. Okay, I had to find the program for the logic analyzer. Okay.
If you want, okay.
Open capture. Where the heck I put it? In temp. Be patient. Here it is. Okay, let me take this one. Okay, what is this? Those are signals I measured using the logic analyzer on another radio, actually, not exactly this one, but one are on I2C bus, which goes from the microcontroller to the radio chip, because that radio has a dedicated integrated circuit for all radio management. And the other one is the data communication between the microcontroller and this chip, which is used for digital DMR protocol encoding. It's connected to the microcontroller in two ways. One is data for voice encoding and blah, blah, blah. The other one is control, because the microcontroller has control on this chip, on the internal configuration of this chip. And to effectively be able to transmit, I had to sniff data communication on an SPI bus between the microcontroller and this chip here. Now I'm using the proprietary tool. I also have SIGROC, which is an open source tool. So just because I have the tool for my analyzer, the proprietary one does not mean you have to.
Yeah, SIGROC works perfectly well.
Exactly.
And,
with my same logic analyzer, by the way. I mean, in mine is just a matter of like habit, in some sense. Okay, what we have here? We have up here we have the I2C bus. Also, keep in mind that you can do this kind of reverse engineering and analysis also with an oscilloscope if your oscilloscope has protocol decoder like mine, and nowadays almost all the scopes have protocol analysis if they have at least 2 channels. Okay, this is SPI bus. I do not go too much in details on how this bus works, but anyway, I have I2C analyzer on this bus. You can see that start condition data is transmitted. Here is listed. If you search for the data sheet or for some information and you look in firmware, if you do not have data sheet, you can see, for example, that this is the slave address, this is the register, this is data, and so on. Another point, here we have the SPI bus. I have no analyzer hooked, but I can hook it. Enable is channel 2, clock is channel 3, you see it has the shape of a clock, and the channel 4 is master output slave input, data transmitted from the MCU to what do you want? Oops, none. Okay, here it is. You set it to hex because it's. You remove this one because it does not make sense. And here you have data transmitted. For example, I mean, you cannot see it very well, but this 82 in hex value, 05, 40, and so on. And then again, by reverse engineering the firmware, by reading the data sheets, if you have then you can try to understand what is going on. Another interesting thing which happened to us is that on this MD380 radio we have HRC 5000 integrated circuit, and the documentation for that integrated circuit is very, very poor. I mean, you do not have all the register listed, and okay. However, we have from another project, we were able to recover a more detailed datasheet and information for another chip, which is like the evolution of this one, which is HRC 6000. And we were able to use the datasheet for the other chip, which is in some sense compatible, to understand and to compensate for the lack of information in the one for this one, just by comparing. Because, for example, you see here, let me take one random transmission. Okay, is 82, 1B, C0. Let's say, for example, that 1B register is not listed in the HR 5000, but is listed on the other one. Just by analyzing this register and the content of, of what is written to that register, you can be able to understand if your assumption is true, and if effectively those two registers are the same, even if are in two different chips. So the point is, if you do not find complete datasheet for something, look also for datasheet of near chips. For example, chips of the same family. Just as for hardware, if you have the schematic for one kind of radio, which is like a sibling of a radio or substitute radio for device you want to reverse engineer, use it, even if that schematic is not exactly the one of the device you are trying to study to analyze the behavior. Because there is the great possibility that there are contact points between the two devices, which for sure help you to understand better the behavior, the hardware functionalities, and so on of the device you want to reverse engineer. Just to give you an example, we started with MD380, and just by equivalence or partial equivalence, we were able to reverse engineer MD380 UV, another version, and apparently completely different radio, which is made for vehicle use, which is completely different. Is this beast here? This is not here. Is not this one. This one is not this one, but they have the same hardware inside. So by looking at the schematic of this one, we were effectively able to reverse engineer that one, just by comparison and exploitation of points of contact. This said, back to you, Nizzo.
This does not happen by chance, by the way, because it's caused by how especially the Chinese market works, where you have small companies which share the same designs, because in the Chinese market, while, for example, in the Western market, a company tries to build his own intellectual property and try to keep it as close as possible, not to share it unless it is for big money. In the Chinese market, all the companies share the same intellectual property. Therefore, they can go to market very quickly by reusing available designs. And this is advantageous also from a reverse engineering standpoint, because by reverse engineering one device, you get many devices, information for many devices. So this is good because you have to do less work and you can reuse existing reverse engineering findings for your device as well. So when you are, the device you are trying to reverse engineer comes from the Chinese market, try to look for clones of the device, to rebrandings of the device, and see if those maybe have already been reverse engineered or documented, maybe better than your own device. And did we already talk about the FCC?
Nope.
Okay. Time to talk about the FCC.
Time to talk about the FCC.
So the
FCC
cool
database.
Thing, yes.
Take the screen if you want, by the way.
Okay, yeah, sure.
Giving you the screen.
Oh, I can just share up. Okay, no, it's not a good idea to mix. Not a good idea to mix resolutions. So let's just do this on a single screen. Okay. Perfect. Okay, so one cool thing about that the American government did is that they require every device to be sold inside the United States to pass, sorry, not every device, but every electronic device that can emit some radiations.
Some radio stuff, something.
Yes, but okay, so
even laptops are
yes.
susceptible to transmit radio frequency stuff.
I believe that's every electronic device, but if you explicitly transmit something, so if you are a radio, you need a separate license. But nonetheless, they require this certification to for every device that has to be sold in the American market, which is good because it's something mandatory, and people often might do want to sell to the American market. So you find the FCC certification for all the devices probably that you own. And this is very interesting because as part of the FCC documentation, you get well, the name of the device, the serial number, but also more importantly, pictures, internal pictures of the device. Even and they often come out before the device is put into market. So this is also useful if you want to stalk your favorite manufacturer to see if they are pulling out some devices. Then you might see under which name they publish to the FCC database, and try to see if they are publishing some new designs. That's something very good, very interesting to be done. And also is also done by other people. So this website, which we will put in the slides, fccid.io, is a searchable FCCID database, which is cool because you can Google basically either a company or the FCCID, and you find the FCCID in the label of the device, because you have to declare it when you market when you sell the device in the United States. I don't know if this is visible, but I have the radio in my hand and I can search this exactly ID. So as you can see, sorry, the cat is controlling the PC now. As you can see, what comes out is TYT electronics, but don't be surprised if what comes out is a different name, because this is not the actual name of the company, it's the name under which the company submits the FCC filings. And you get some, this is also a transmitting device, so it has to declare it. And by checking this, you can see if your device maybe is able to transmit in bands to which maybe you didn't think it could transmit, simply because the manufacturer blocked it. And also he's declared the power, the output power of the transmission. But more importantly, we have here internal photos and external photos. This is especially useful when you are investigating for devices which still haven't come out, or simply you want to check whether the device you are searching in the FCC database does actually match with what you expect to be. But also you have internal photos. So if you, what you will find here is a PDF document which will contain a detailed picture with a scale also of the device. It might not be identical to your device. For example, this one is not the same as my radio, but I believe that what they are certifying is maybe the PCB. So if you have several radios which share the same hardware but might appear different aesthetically, those will be listed under the same FCC ID. And here, you see the pictures of the PCB, which is very cool because I could check this even before purchasing the radio. For example, several things like the microcontroller is very easily recognizable. I can see from this distance that this is an STM32 because there's the ST logo and the ARM logo. So, you can, for example, check this in advance before purchasing a device which you want to reverse engineer, to check if it will contain a microcontroller that you will support, you will be able to manage. For example, very cheap devices often are based on an infamous CPU which is called 8081, which is exactly a clone of the old Intel 8081, which is an awful thing because, I mean, you find that on the market because basically the licensing for that CPU are expired, are long expired, since the CPU is from the 80s. So the design is cheap, and also several Chinese companies manufacture the silicon for that CPU for a chip. But the hardest part is that the compilers and compilers for that CPU, they are not open source. You have to pay for them, and so it's not a nice CPU for which to write your own code, an 8081. And that CPU is probably, you have probably on your desk many devices containing it, because if you take a USB drive, if you take a chip keyboard, probably this calculator has one on it. So everything which is let's say under $10 and does something probably contains a microcontroller, which is an 8081. So yes, apart from this, the cool thing is that also you get pictures from this side, which to actually obtain this, you have to desolder one connector. So they did it for us. As you can see, here is you can maybe also read the serial part, STM32F405, which is the proper part number for that radio. Okay, so yeah, so FCC is your friend and use it. So I believe that's it for the FCC. Should we?
If you want, I have another example.
Yes. You want to share
something which happened like to us for another radio in like less than 1 month ago. We found this ANG7 radio. Let me see. Here it is. No, that's FCC again. Anyway, we were exploring for other hackable radios. We found that one. Now I do not exactly remember the part number, but anyway. And we looked for FCC, which is basically the first thing we do when thinking of porting our work or to do some hacks to extend our work to other platforms. Internal photos, download PDF, which is better. Open it. Here it is. Open view.
You know, there's TYT there.
Yeah.
The brand is the same.
The brand is the same, but here it is. This is an STM32 again. So, and the fact that there is an STM32 automatically makes you say, okay, we can reverse engineer it without pains. It's easy to reverse engineer this kind of device up to a certain point, but anyway, we can do it. You go ahead, you go to the RF stage, and you see 80. This chip here is the okay. This is the radio on a chip, which I was talking about like 10 minutes ago. And again, this is something which allows you to say, okay, we can do it. It is something on which we already worked. We can try to go ahead with our reverse engineering. This is just an example. I mean, it became like one of our habits to check on FCC if a device can be effectively reverse engineered, or it's easy for a to do. It's if it can be easily reverse engineered just by checking an FCC database and to look to the internal photos. Okay.
So
now firmware time.
Okay, so yeah, I will share my screen again. So now let's spend some time talking about actual firmware decompilation. We didn't make it into, which didn't make it into yesterday's presentation. So let's do a kind of a deep dive in Goodra. So what is Goodra? Goodra is free and open source. No, I believe it's not FOSS. Is it FOSS? Yeah. For sure it is. Yeah, okay, so it's free and open source.
It is hosted on GitHub.
Okay,
perfect. Quite sure it is hosted on GitHub.
Yeah, we should check the license, but nonetheless, it's for sure open source. I don't know if it's free, but it's open source software. And it's a decompiler, and it's kindly brought to you by the NSA, which is the National Intelligence Agency of the United States. What we will see is basically how to do the jailbreak of yesterday. At some point, we just said, okay, yeah, we discovered that the point to patch is this. And now we will see from scratch how to obtain that knowledge. Just having the binary of the bootloader in our hand and a bunch of information about the architecture of the device which we are reverse engineering, that we can easily obtain by either the datasheet of the CPU or just by, you know, observation. So okay, so let me first begin with how to load a binary into Goodra. Let's start from the beginning. So you can download the Goodra from their website, or it is hosted also on GitHub. Goodra is written in Java, so you will need a Java virtual machine to run it, and you run it by it also. The cool thing that is written in Java is that it also runs on Linux.
But by the way, you can install it with your package manager on some Linux distribution. At least Arch does it, and Ubuntu, I think, the same.
Okay.
So you do not even have to.
Yeah, so probably you don't even have to download it. And so you can create a new project. This is just an empty project I have created, and then the empty project won't contain anything, but we can import the executable from the file menu. And right now we will choose the recovery that we dumped from the radio. By this can be obtained even without jailbreaking the radio, because the recovery memory region is not read protected. So you can get this using DFU from the the radio in ST bootloader mode. So you open the radio, you bridge boot 0 pin, which is exposed as a pad, to 3.3 volt. Then you boot the radio, and the radio will appear through USB as a DFU device, and you can use ST tools to read for example, the first part of the memory which contains the recovery. So once we get this binary image, which we can first look at it. So so if we take a look at this, I'm using XXD, which is a nice binary visualizer. However, it produces some text output, so I'm piping it to less to have a better paging. Is it the correct image? No, probably not.
Why not opening?
No,
you were opening the SWD file, the SVD file.
Okay, now this is the recovery from Taitira, which is the manufacturer from the radio. So if I open it, I will see that here we have, the columns I was talking about yesterday. As you can see here, you have this 0008 nibble, which repeats. This is because this is the interrupt vector table of the CPU. And all of these are little endian encoded addresses, which are the addresses of the various handling functions, like, the reset handler, the bus fault handler, the memory error handler, and non-maskable interrupt, everything that, all the handlers. So when you see something like this, you know that you are at the beginning of a binary image of a microcontroller. This is an STM32. However, this payload is typical of the ARM Cortex CPU, but also other architectures, like, for example, we have another radio, which I don't have here, that it's based on a CPU by Renesas, but that radio has a similar pattern. I can show it. Yes.
Go on. Sorry.
So this is a different CPU. This is a binary image for a Renesas RX architecture. So this is not even based on ARM. It's a totally different instruction set. But as you can see, it begins with a very easy to recognize pattern, because even this CPU at the beginning has the interrupt vector table. And another thing which can be used to investigate a binary image is an entropy plot. And you can do this using binwalk. Okay. With the -e option. Okay. It will pop up a plot of the entropy. Now, for entropy is a weird term. For those of you who didn't already do the cryptography course, entropy is a proxy for randomness. So how much the data that you see on a binary are close to a random number, or to a random sequence of number. Now, the information that you can derive from an entropy plot are several. For example, here we are seeing that the image ends at roughly 24 k kilobytes, because after this, and we can check this by inspecting the for example, with XXD the image. If we go at some point, we have only Fs. As you can see, the image ends here, and a constant value has an entropy of 0. So as you can see, from here on, you have a constant byte. In our case, is F, but it could even be any other constant thing. But the important part is that there is no information here. Okay, this is just constant data. But so you can understand, in the case of Silvano's example, you would have seen several peaks, several high parts with some intervals of 0 entropy. So you can easily identify if your binary image, your dump, is composed of several different portions, several different sections. Another thing which is very useful when observing entropy plots is to detect if your binary data is encrypted or not. Because encrypted data, when looking at it in binary, are very similar to executable data, because humans cannot distinguish. I mean, the human eye cannot distinguish easily binary code from random data. But if you plot the entropy, you will see that if the binary or sections of the binary are properly encrypted, I mean, with a serious encryption method like AES or even a random pad, you will see that the entropy is close to 1. So encrypted data has very high entropy because it resembles random data. So in this case, this is not encrypted because the entropy is too low. It's not 1. It's not like 0.95. Is approximately 0.8. So this stuff is not encrypted. So once we have our binary and we have recognized that also if it's encrypted, if it's properly encrypted, you should not be able to see this column column-like pattern, because encryption exhibits the diffusion property, so you should not be able to recognize patterns. But once we were able to see that this binary seems not encrypted and seems to contain some ARM code, and we know this because the CPU is an STM32, we can try to load it into Goodra. So we use the file import file option. We select the binary image. And here we have several options. The format will be raw binary because I mean, it's not an executable for Windows or for Linux. It's not an ELF RP. It's just a raw binary. And language, here you will have to select the architecture of the binary. Here you have all the architecture supported by Goodra, which are a lot, really a lot. And we will go for ARM, and in particular, since we notice that all the pointers here they are encoded in little endian, so this is the last byte of the pointer, and this is another last byte. All the pointers are odd, therefore we know that the CPU is executing in thumb mode, is executing thumb instructions. So we will use the ARM Cortex thumb basically instruction set. For the endianness, the default endianness of ARM CPUs, modern ARM CPUs, is a little endian. But we can confirm this by looking at these addresses, in which clearly this is the most significant byte and this is the least significant byte. So we know already the endianness. Messing this will result in a completely wrong, I mean, Goodra will probably try to decompile the thing, but will output instructions that make no sense. You will at some point develop the skill for understanding when the decompiler is messing things up, because programs, they usually are composed by normal instructions. So if you see just some weird conditional loads and nothing else, then probably the decompiler is messing with the compilation process. If you see some ordinary instructions, then probably the compilation is good. So right now we select this, and most importantly, there is the option field, which is hidden. So you have to pull it out, and allows to set some more options, which are easy, because otherwise changing those afterwards is a mess. So from the fact that the interrupt vector table seems to begin, I mean, all the pointers that we have here that we listed before, I have here a screen, yeah. So all the pointers that we have here seem to begin at 0800. I mean, this is from the RAM, so we will consider this later. But this one, all these pointers, which are pointer to the interrupt handler, they seem to begin at 08000. Okay, so we can use this information to load this address, this binary, at 08000000. So by loading, I mean, since this is at the beginning of, basically, this is the beginning of the binary, okay? But if all the address are based to that offset, this means that this binary probably is placed in the memory of the microcontroller at that offset, 080000, okay? So if here we have 70, this when the binary is loaded into the radio, will become 08 and then 00070. Okay, so we use this as a base address, and then we leave all the other fields as default, and we can set a label. We will say that this is the flash. Okay, so we import the project, we get close to unreadable output. We double click the binary, and Goodra says the binary has not been analyzed. Would you like to do it now? And we will answer no. This is because we will do something more interesting before letting Goodra analyze it. We will, for example, prepare the ground to make sure that the analysis process can do a better job. The first thing that we will use to do that is called Svd Loader. So Svd Loader is a script for Goodra. Goodra is scriptable, and it's scriptable in Python. Luckily, they decided this instead of having us write Java software for scripting. So this script, it takes the well-known addresses of many MCUs, which are usually defined in a format, text-based format, which is called SVD. Okay, and it lets you import those addresses in Goodra, such that when for example, a load address tries to fetch data from a certain location into the address space, instead of just seeing, as you would see, okay, we still don't see here, but I can see an example on the Svd Loader web page. So this is the before. So what you see here is that the software is assigning to this location in memory, the content of this other location in memory and this other location in memory, which is not like the best thing to read, but maybe those location in memory are maybe they match to some peripheral address of the MCU. For example, in this case, this matches to the CRG top sysstart register. Okay, since we know those registers in advance because they are given to us by the manufacturer of the microcontroller, then we might use that, load that into Goodra to gain a better decompilation. To find the SVDs for your platform, you can go either to the manufacturer website, or there are some repos like these which host hand patched versions of the SVDs, and you can find those for many different platforms. We have the F401 for the STM32 of 05.
Yeah.
Okay, so I should have.
I mean, that does not change almost anything, but
whatever. I will pick one, and I will load it. So first you need to install Svd Loader, but the procedure is easy. You need to go here into the script manager, and you need to go here where there is the manage script directories, and add the location where you cloned the Svd Loader project. Okay, and then you just have to refresh so that the Svd Loader can be loaded, and it will be listed here. As you can see, this is the script for loading the SVDs. So to use it, I will double click it, and he will ask me for the location of the SVD files to be loaded. So now what I will do is I will load, it was a F05, right? But this is the wrong one, but it will be very similar. So I will load the svd file.
Yeah, there is almost no difference.
Okay. And as you can see here, you get a new namespace inside the Goodra project, which contain all the peripherals of the standard SVD. Okay. So now what we can do, we can, before, another step to be done before letting Goodra analyze this is to fix the memory map. So we know, yeah, so this is a bit, we know, for example, this is the segment that we loaded from the flash, but we have also some other segments. You know, the peripherals are mapped into memory at these locations. Just a minute. Okay, so as you can see here, the are the address spaces at which the various peripherals of the STM32 are mapped. But something is still missing. We are still missing the DRAM. So we will, sorry, the SRAM. We will add a new block, which is the RAM, and we know it from the fact that some addresses like this one, they load from a RAM. So we know that 20, we hypothesize that 20.00000 is the beginning of the RAM. So we put as a start address 20.0000000. And the length now it's, as I said before, we can get it from the datasheet, is 192 kilobytes, which is
wait, is 128.
So, okay, perfect.
Because
it's 128.
Yeah, because you hit in one of the weirdnesses from ST microelectronics.
The close couple DCCM. Yeah. Okay.
Yeah,
so
it's 128K of RAM plus 64 of CCM at another address, completely another address, which is 10000.
We will add both. So we know that this one has a size, the main RAM has a size of 2 and 4 zeros. So while adding it, RAM, so this is 0x20000000, and this 20000. Okay. And then I will add also the DCCM. Sorry, is it DCCM or ICCM?
CCM.
CCM.
Core coupled memory.
Which will be at 10000000, right?
Yeah.
And will be just 64, which is
which is one is like the other one is yeah,
like this.
Is the half of the other one.
By adding these segments, when a load instruction, for example, takes a value from this an address included in this range, instead of just throwing an error and say, okay, this instruction, I don't know where it loads things from, it will create a reference inside the flash, inside the RAM or the CCM. So all of these will become will give to a better decompiled binary. So right now we can start the analysis process. We will just leave the defaults. And as we can see from the sidebar, which we can pop out. So tools. What is the sidebar? I can't find it. No problem. Should be. By the way, okay, also this is the sidebar. It was already active. So Goodra is slowly starting to recognize functions inside the our binary. So I hope it did a good thing. So as we can see here, is already recognizing that these are addresses and is also decoding that from the little endian encoding. So what we will do now is, what we want to do now is we want to basically infer. Here it is. To jailbreak the bootloader, we want to find the piece of the binary where the RDP protection is enabled, which we know that is where 55 is stored inside this address, which, since we loaded the SVD package, will be identified by the flash OPTCR symbol. Okay. So we have to find the place where 55 is stored inside flash OPTCR. To do this, we will start from the namespace and locate the flash OPTCR memory location. So it's under flash, and it will be here, flash OPTCR. Here it is. So if we hit the right button and select references and show references to flash OPTCR, we are asking Goodra to select all the loads and store and all the instructions which are using that address. And among all of them, there is one, where is it? Which is a write.
Here it is. Above.
Is it this, right?
Also slightly above.
Okay, so there are many of them, but I believe this one is the right one. I'm doing this live, so I double click it. So when I double click it, the Goodra goes to that point, so shows me this is the decompiled. So these are the binary instructions, and then on the right you see the C code. So as we can see, now it's not that visible, but should be, this is a strb, which for those of you which are not familiar with the ARM instruction is a store and has a byte granularity. So this store a single byte into the address. The address on which it is stored is this one, which is taken from R1 with offset 0, but Goodra is smart, so knows that this corresponds to flash OPTCR. Okay. So we know that this stores the content of the register R0 into flash OPTCR. And if we select the various instructions, you know, there is this red marker which changes on the decompiled code and we know that this store corresponds to this C instruction, which is, as you see, an assignment to an address. Okay. So we can, for example, use the L rename global to actually give a proper name to this variable. For example, OPTCR or flash OPTCR. Okay. So that this variable in all its uses across the project will have a proper name, a meaningful name. Okay. So we know that we are storing to flash OPTCR basically. Okay, this is a bit broken. Oh, so probably this is not the right function. Yeah, so this is just storing the same content with a bitwise.
second bit
Okay.
is a 2. That one is
Yes.
what's doing that.
So probably this is not the right function because that one was.
Datasheet is your best friend. Always. Let me check while you go on.
Meanwhile, I will find some other occurrences of this. So
Flash.
we have several writes.
Flash opt key register.
Let's see
No, opt
this other function. So as we see, we have many functions which sets just 1 bit. So again, let me check. Flash OPTCR, we have a read, write, write.
Okay, that one is option start. This bit triggers a user option operation when set.
Okay, so but I believe
so you were closed. You were close to that.
I believe I believe
maybe
you
have to jump to the callee of that function. Maybe.
Okay, let's see. You know, when you do
to the
reverse
caller,
engineering, yeah, when you do reverse engineering, you have to poke around and see where stuff comes from. So this is another function which stores into flash OPTCR +1, which might be it because we want to set the first byte, right, of the OPTCR
+1 register map. Is a strb. Yes, store byte.
This is a store byte. Yes.
So it's setting an WRP maybe. Let me see. Maybe setting the write protection. Maybe.
But really, start when you do reverse engineering, start renaming everything, even when you have just wild guesses about what something do. It's better to have that to leave a trace, otherwise you might really get lost inside the compiled project. So here, if we try to follow the color of this function, the colors of this function to see, because this one takes an input parameter, which is then stored inside OPTCR +1 if a certain condition is met, okay? So here, the function that calls this one defines the byte that will be stored in here. So we will hit again right button and select define the reference to the function name. I've just given that function name. We have just one reference, okay? And as we can see, yeah, I found it. As we can see here, we have the function set OPTCR +1, which is called passing a 55 as its argument. Now, this is more reliable than this. So this might be wrong. There are more chances that it's correct, but also this can be wrong if, for example, the coding is faulty. So take what you see with a grain of salt, because you know, this is just a decompile, it's not the actual source code. So if you see something weird, it's probably something weird. Don't panic, don't get mad. So, but what we have found here, this 55, and I can check this, the offset of the binary should match with the one which I've highlighted yesterday, is 080044A8. Which is exactly what I was mentioning yesterday. So we know that this 55, which is the one which is stored inside here, actually controls the activation of that functionality. So one thing we could do is we could simply take this location back into the binary. So go into 080044A8 080044A0. Remember to put 0 instead of 8 because otherwise 080044. Oh, sorry, you don't have 8 here, so this is the correct offset. And as you can see here, we have a 55, and these bytes correspond to this because we have FF, FD, F7, A0, FD, FD, F7, A0, FD. And then this 55 is this 55 that in turn becomes this 55. So if we patch this binary and you know, there are many ways to patch the binary, but I found one which was pretty good, but I can't remember it right now. If I will do later on, I will edit the slides. By the way, if we put AA instead of 55 here, we will obtain a jailbroken bootloader, and we can put it back on the radio and have a jailbroken radio. And this is exactly what we did. But for example, another route could be to inspect here. For example, this function is enclosed in a conditional statement, which is driven by this variable. So by checking where this variable comes from, we might find other way to circumvent this RDP. Maybe, I don't know, hitting a certain button while the radio turns on, disable that bit, or maybe that the radio reads that value from the flash. So you have while reverse engineering, you have many ways to do stuff. So since we have only a few minutes left, I will just go over the few more things that I have to say about Ghidra, and then maybe we have some questions. So another thing you can do in Ghidra, for example, if either you were decompiling that project with a totally legit version of IDA, you can export the symbols from IDA and import those into Ghidra. I've put here a gist that you can use to do so. But for example, the GitHub MD380 tools project as really an act of kindness with respect to other reverse engineer, it published into its repo the annotations, which are basically as you can see here, the memory addresses with relative names of all the firmwares of the MD380. And I encourage you, if you start doing reverse engineering of a device, to give back to the community, to publish for example, the symbol locations of that you have found, because those might be helpful for other people, which will start reverse engineering from where you left instead of just starting from scratch. Also, you can do a collaborative setup with Ghidra. Ghidra supports many to be used in a client server mode, where you have a Ghidra server, which is still written in Java and which runs somewhere, and clients can attach to that server and open a remote project. The cool thing about this is that when you are working in a team, it's painful to keep reverse engineering synchronized, because you will be producing different projects which you will be giving different names to the variables. Instead, if you spend a bit of time in setting up a shared Ghidra, you will be able to share the reverse engineering effort, which is cool because that is a hard part of the developing of open source software for a proprietary platform. So why not share that effort and do that together? It works more or less similar to Git, where you can do a checkout of a project. You can at the end commit your changes, and you need an exclusive checkout to do harder stuff like modifying memory layout. So we use this for the OpenRTX project, and it works quite well, provided the initial difficulty of setting up, Java binaries. But to ease the effort of setting this up, I've put in the slides this Docker image, which contains basically the Goodra server and all the necessary tools to manage it, to create users, to give access, and so on and so forth. So with this Docker file, you can have an easier life in setting up a shared Goodra instance. So I believe we ran out of time. I don't know if we might spend a few words. Maybe, I don't know, Silvano, should we skip the AT in sequence and just talk about PolyHam?
We can. It's just how we reverse engineer the piece of software with the help of hardware. But
yeah, maybe we can.
It's nothing. It's not rocket science. So we can skip it easily, no problem.
Okay. Just a final word about PolyHam, which is a newborn association in Politecnico di Milano, which is basically its own. The Politecnico di Milano owns Ham Radio Club, and we recently got even a call sign from the Italian Ministry of Communication, and we also have the general authorization of transmitting. So if you choose to become a ham radio operator, you can join the club and you can transmit using the call sign of the Politecnico. But we also are active in. We plan to do activities in many fields like digital experimentation, HF communication. The cool thing about this is that you can jump into the experimentation part of the radio without having to purchase expensive equipment like an HF radio, because the radio club will have some equipment on its own, and thus it would be a cool way to do things which would be difficult to do on your own. For example, the radio club will probably in the future have access to some physical place where to put the huge antenna which are required for the HF communication. And this is just another reason. If you're interested in this project, contact me or Silvano, and we will talk more about this. And I believe that's it for the second episode of the ReverseIt course of 2021. If you have questions, maybe we can read some of those now. Otherwise, feel free to drop me or Silvano an email. And thank you for attending. Don't forget to sign the self-certification, which will help us in delivering more courses like this. And happy hacking to everyone.